So although the original problem just asked us to decompose these vectors into x and y components, I'm going to go a step further and find the resultant force, usually denoted as F sub r, and I'm going to describe it in polar form. So if you go back to the actual lecture that I did on this learning module, we said that the real advantage of breaking vectors down into rectangular components is that addition, rather than being that cumbersome geometrical process, just starts to resemble the addition of scalars. So namely, if I want to compute the resultant vector, all that I need to do is take the x component of f1, the x component of f2, the x component of f3, add them together, and that's my x component of the resultant. I show that by scaling by I hat, and I just do a similar thing for the y components, right? Add the y component of f1, f2, and f3, and that will be my answer. Now, typically, if you notice, again, this is a rounded number. So if you were asked to do this calculation from scratch, you wouldn't work with these rounded quantities, but I'm going to in this video just for convenience. So I'm going to take and say that the x component of the resultant. Now, if you haven't seen software beforehand or any kind of programming, that's okay. I'm just going to store my answer in this variable, and I'm going to add the x component of f1, which was 0. When I add on a negative 297, that can be just more simply expressed as subtracting 297. And then I'm going to add on the x component of f3, which was 348. So that's going to give me 51 newtons of force in the horizontal direction. And for the vertical direction, I'm going to add 320, 297, and 464. I'm going to get a result of a little over a kilonewton of force. And if you look at that original diagram that we were provided, it's not surprising that the y component of the resultant force, which is just to say how much that thing is being pulled up out of the ground, is much greater than the horizontal component. Because, and as you would want to design this in a practical scenario, effectively the horizontal components of F3 and F2 are kind of tending to cancel each other out. And of course, F1 doesn't contribute to any horizontal force acting on this connector. So that is the resultant force expressed in rectangular form. So let's actually draw what it would look like. And I'm going to draw a big coordinate axes, and I'm only going to draw quadrant 1 and quadrant 2 because technically I only need quadrant 1. But this vector, the way that it looks, and this is not to scale, so don't get too picky with me. This is the resultant. It has a magnitude that we're going to determine in order to express it in polar form. And it can be decomposed into an x and y component that look like this. And now we know the x component has a magnitude of 51, and we know the y component has a magnitude of 1081. So this is a right angle, right? Because by definition, the y and x components are perpendicular to one another. I can determine this hypotenuse of this right triangle through Pythagorean's theorem. I take the square root of the sum of the x and the y component squared. And in terms of getting the angle, now I want to be careful here, and this is kind of why I was showing you why oftentimes a drawing is beneficial. If I take and compute this theta, right, and maybe a better way just to not confuse you, I'll call this an angle alpha. Alpha would be the inverse tangent of 51 divided by 1081. But if I do it this way, and that's okay, based upon the way that I have my drawing, that looks like a convenient angle, I'm going to have to make an adjustment because technically the conventional angle that's usually reported when a vector is expressed in polar form is measured from the positive x-axis with a counterclockwise rotation to the line of action of that force vector. So an alternative way you could do this, rather than computing alpha and then saying theta is going to be 90 minus alpha, is just redraw your force triangle, and rather than drawing it, let me show you here. Draw it like this. It's got that very small x component, very big y component. This is totally not to scale, but that's okay. This was 51 units of force. This was 1081 units of force. And now I get the traditional approach that I usually use for determining the angle, which is the y component divided by the x component. So this is Fy divided by Fx. So if you just use the formula for this, you are okay because you're in the first quadrant. So I'll show you that you get the same result either way. So let's go to MATLAB to make a calculation. Again, I don't want to confuse you. If you're like, hey, I thought we didn't have to know MATLAB for this class, you don't. That's okay. If you want to, even though I don't think we have a license here at SAC, you can. I know many of you have some affiliation with UTSA. There's a site license there, or you can access the online version of MATLAB for free. One of the nice things about MATLAB is it already is putting this in engineering notation for me. I'll take 3 sig figs and round, so I get 1.08 times 10 to the third newtons, and we'll put our prefix on in a minute. So let's compute our two angles here, alpha and theta, which we spoke of. Now, again, this is something, since we're dealing with angles, we want to be careful the mode that our calculator is in. In programming language, usually you denote mode by adding a D in there. If you're using a calculator, you know how to do it. So I got 2.70 to 3 sig figs degrees. And if you look at our drawing, we knew that angle alpha that we had to find would be very small. Or alternatively, if I wanted to find the angle directly theta, I could just take the arctangent of the inverse of that, and I will get 87.3 degrees. And I won't insult your intelligence, but look, if you add those two last values together, they of course do add to 90 degrees. So let's talk about how you could actually write your resultant here. I can write that FR has a magnitude of 1.08. Now, rather than writing 10 to the third by convention, like we talked about in chapter 1, we'll use the prefix kilo newtons, and it's going to be at an angle of 87.3 degrees. And I chose to use theta because that is the conventional angle that we report. The reason that I kind of went about two ways of doing it is showing you that sometimes you make a drawing that's just convenient to you, or the first thing you draw, that will allow you to get the information you need, but you have to do an additional step. And just to be clear, for those of you that prefer to just go to formulas right away, you totally could have done that in that case. And the formulas are Pythagorean's theorem, and this always works regardless of which quadrant you're in. And for the angle of interest, you can just take the inverse tangent of the y component divided by the x component, as long as you're in the first and fourth quadrant. If you're in the second and third, you'll have to manually do some adjustments like we showed in the prior video. So hopefully this will be beneficial to getting you started on your second homework. As I mentioned, I kind of broke it down. We're only going to do half of chapter 2 this week because I know a lot of you are only going to start working on the course material over the weekend, and I don't want to overwhelm you. Now, we are going to be a little more rushed in the coming weeks, so just be prepared to maybe work a little harder for weeks 3 through 8 than we did this week. But the good news is I will take this weekend and I'll get all the material for next week up in advance. That way I can accommodate everyone, whether you're working during the week or working on weekends.